Welcome to Fundamentals of Artificial Intelligence. We are looking at knowledge representation and reasoning and have covered propositional logic. In the last class, we introduced first order logic, which is also called predicate logic or first order predicate calculus. We have looked at predicates and functions, looked very closely at quantifiers, for it is the quantifiers that make first order logic more expressive than propositional logic. Today, we will continue our discussion of first order logic. In the previous lecture on first order logic, we had discussed the syntax of first order logic. We had looked at how to translate an English sentence into a logical statement. We had looked at negation of quantified sentences, and we have seen how one could distribute the quantifiers over the conjunction and the disjunction. The treatment of semantics, however, in our discussion in our last class was quite informal. In this lecture, we would provide a precise definition of meaning, what we refer to as declarative semantics. We would understand a concept called conceptualization, and as an example of knowledge representation, we would work through two example problems, one a blocks wall example and another a simple genealogy knowledge base. We have argued that intelligent behavior depends on the knowledge that an entity has about its environment. It is important to realize that this knowledge is declarative, that is, it is by its very nature expressed in declarative sentences or indicative propositions. Much of the knowledge of the environment is descriptive and can be expressed in declarative form. Formalization of knowledge in a declarative form begins with a conceptualization. A conceptualization is about identifying or presuming what are the objects that exist in the world and what are their interrelationships. Now, here the concept of object is very general. Objects can be anything about which we want to say something. Let us look at a very simple toy conceptualization of the world, which is referred to as the blocks world. We have 5 blocks on a table, and here is the blocks world scene. Now, one needs to realize that not all knowledge representation tasks require that we consider all the objects in the world. In this example, we will consider the objects A, B, C, D and E, which are the blocks, but we will not consider the table as an object for this illustration. So, we have a concept called the universe of discourse, which is about the set of objects about which knowledge is expressed. In this example here, the universe of discourse is a set containing the 5 blocks. Apart from the blocks, as I was referring to, many conceptualize the table on which the blocks are resting as an object as well. We leave it out here. In this example, there are finitely many elements in our universe of discourse. One needs to realize that this need not always be the case. In many problems, which is common in mathematics, for example, we consider the universe to be of infinitely many elements. Like, for example, the set of integers as universe with infinitely many elements. One important concept that we have looked yesterday is the concept of function. Function is one kind of interrelationship among objects in a universe of discourse. For this Bloch-Wald scenario that we have here, we could have many functions defined, but then only a couple of them would be included in the conceptualization. The set of functions which are emphasized in a conceptualization is called the functional basis set. In this example, it would make sense to conceptualize the partial function hat that maps a block into block on top of it, if any exist. Now, tuples corresponding to the hat function would be the pairs BA, CB, ED. Let us look at one of them and try to understand what we mean by this. So, if you think of hat as a function, it would take one object and it would return another object, and in this example the hat maps a block into a block which is on top of it. So, if you take B here, the hat function would return to us an A which is a block on top of it. Similarly, for CB and the pair ED. The other kind of relationship among objects in a universe of discourse is the relation. In a spatial configuration of the Wald's block, there are a number of meaningful relations. We could talk of blocks being on the table, we could talk of blocks being on top of one another, so on and so forth. Here we consider a relation called on, which holds if and only if a block is immediately above the other. We talk of a relation above, which is between two blocks, if and only if one is above the other. We then have a unary relation, clear, to mean no block is on top of the other block. Out of these numerous relations possible, the set of relations emphasized in a conceptualization is called the relational basis set. For the scene, elements corresponding to the different relations are, for the on relation, I have tuples AB, for A is on B, similarly BC and DE. For the above relation, I would have tuples AB, BC, AC and DE. Thereafter, I could have tuples for clear, as I can see it here, nothing on top of A. So, I would have A as an element of the clear relation and D. I have one more relation called the table to mean an object is on the table, and here I have the elements as CE. Now, if you look at the two relations on and above, you could see that in terms of the on relation is a subset of the above relation, and the on relation is therefore less general than the above relation. Given the concept of a functional basis set, a relational basis set and the universe of discourse, we are now in a position to formally define a conceptualization. A conceptualization is a triple consisting of a universe of discourse, a functional basis set for that universe of discourse, and a relational basis set. Coming back to the Bloch-Wald scene that we are conceptualizing, the following triple is one conceptualization of the blocks world. I have the 5 blocks A, B, C, D, E as the objects in the universe of discourse. As for the functional basis set, I have a function hat, and as for the relational basis, I have on, above, clear and table, the 4 relations. So, this triple is a conceptualization of the blocks world here. Although we have written names of objects, functions and relations here, one needs to realize that the conceptualization consists of the objects, functions and relations themselves. Now, what makes a conceptualization better than another one? There is not a comprehensive answer for this question. However, one noteworthy issue to look at it is the issue of granularity or grain size. Choosing too small a grain size can make knowledge representation tedious. Like here in the blocks world, if you think of objects in the universe of discourse in terms of atoms, you would see that you would have a huge number of elements to deal with when the only task is about stacking one on top of the other, and therefore looking at them as blocks would suffice. However, if we were thinking of looking at the chemical properties of these blocks, then the grain size that we have considered of the objects as blocks would be too large a grain size, and knowledge representation would be impossible. So, for declarative semantics, we assume the perspective of the observer as shown in the illustration here. We have a set of sentences and a conceptualization of the world. We associate symbols used in the sentence with objects, functions and relations of our conceptualization. We evaluate the truth value of the sentences in accordance with this association, and a sentence is true if and only if it accurately describes the world according to our conceptualization. So, let us now try and understand what we mean by an interpretation given a conceptualization and the elements of a language in which we want to do the representation. An interpretation is a mapping between the elements of the language and the elements of a conceptualization. The mapping is represented by a function of sigma, where sigma is an element of the language. The universe of discourse, for an interpretation I, the following properties need to be satisfied. If sigma is an object constant, then it needs to name a specific element of a universe of discourse under the given interpretation. If pi is an n-ary function constant, then the mapping under the given interpretation should map pi as a function on members of the universe of discourse. Finally, if rho is an n-ary relation constant, then under that interpretation, rho need to be able to name a relation on the universe of discourse. So, let us now come back to the blocks world problem that we were looking at and try to understand what we mean by interpretation. So, here the predicate calculus language that we have has 5 object constants A, B, C, D and E, which represent somehow the blocks in our world. We have a function constant hat and we have relational constants on, above, clear and table. The following mapping corresponds to our usual interpretation for this symbol. So, here under interpretation I, the block A is mapped to the constant symbol A, then we have B mapped to B, so on and so forth, and the function constant under the interpretation have the following tuple, similarly for the other relation constants. This is the intended interpretation, the one suggested by the names of the constant. One needs to realize that these constants can equally well be interpreted in other ways, and we would have a different interpretation of the Bloch's world problem. Now, let us look at what we mean by a variable assignment. A variable assignment is a function for the variables of a language to objects in the universe of discourse. So, in the Bloch's world example, under an variable assignment u, the variable x could be assigned to a, the variable y could be assigned to a, and the variable z could be assigned to b. Given an interpretation I and a variable assignment u, we can now talk of a term assignment, which is a mapping from terms to objects. For example, we have the above variable assignment u, and we have a term hat of C. Now, hat of C designates block B, because the interpretation I maps C, the constant symbol, to block C, and tuple CB is a member of the function designated by hat, and therefore, the term assignment designates the term hat C as block B. The notions of interpretation and variable assignment are important because they allow us to define a relative notion of truth, which is called satisfaction. The fact that a sentence phi is satisfied by an interpretation I and a variable assignment u is written as under interpretation I entails phi u. What this means is that the sentence phi is satisfied by an interpretation I when I have a variable assignment u. Let us look at the Bloch's world and see what we mean. So, here is an interpretation that takes me from the block A to A here and B to the constant symbol B there, and the tuple AB is already within the tuples for on. So, we can write that under the interpretation I, the on AB is entailed. We say that the sentence phi is true relative to the interpretation I and the assignment u. The definitions for satisfaction differs from one type of sentence to another. Here we have only highlighted the main idea. Working through each of the type of sentence is left for the reader as self-study. Satisfiability is also dependent on interpretation. Under some interpretation, a sentence could be true. Under other interpretations, it can be false. The satisfiability of logical sentences depends on the logical operators involved. We will just note here that the universally quantified sentence is satisfied if and only if the enclosed statement is satisfied for all assignments of the quantified variable. The existentially quantified sentence is satisfied if and only if the enclosed statement is satisfied for some assignment of the quantified variable. Now, having understood assignment, we define something called a model. If an assignment I satisfies a sentence phi for all variable assignments, then I is said to be a model of phi, written as under assignment I entails phi. Now, let us look at the blocks world scene and consider the following expression: on xy implies above xy. Now, interpretation I from our blocks world example is a model of the sentence. Let us see how that is. Consider the variable assignment u that maps x to block A and y to block B. Under this assignment, on xy and above xy are both satisfied. Therefore, they satisfy the implication. As an alternative, consider variable assignment u that maps x and y both to block A. Under this assignment, above x y is not satisfied, neither is on x y, and therefore the implication is satisfied. So, we have seen that for all variable assignments, the interpretation I from our blocks world example satisfies this above expression, and therefore we say that the interpretation I is a model of the sentence. We can easily extend the definitions to set of sentences. A set gamma of sentences is satisfied by an interpretation I and a variable assignment written as entails gamma u if and only if every member of gamma is satisfied by the interpretation I and the variable assignment u. And then we could think of a model for a set of sentences. So, an interpretation I is a model of a set gamma of sentences written as entails gamma if and only if it is a model of every member of gamma. So, we have seen that conceptualization is followed by selecting a vocabulary of object constants, function constants and relation constants. We associate these constants with objects, functions and relations in our conceptualization. We write sentences to constitute the machine's declarative knowledge. It is generally true that as one writes more sentences, the number of possible models decreases. Now, the question is it possible to define a set of symbols so thoroughly that no interpretation is possible except the one that is intended? It turns out that this is not the case. There is no way in general of ensuring a unique interpretation, no matter how many sentences we write. Under this scenario, we would now look at an example of the blocks world and try to write down the essential and the general information for these blocks world scene. For the blocks world scene shown on your right, we could write things as on AB, above AB and clear A. We could write similar relations for B and C, and D being clear, we could write clear D. We could write similar relationship of on between D and E and above between A and C. Similarly, we could write that C is on the table and E is on the table. Note that all of these sentences are true under the intended interpretation. Encode some more general facts using general sentences is possible. So, here we have a general statement that relates on to above. If one block is on another block, then that block is above the other block. And we could also write more interesting statements on above itself and show that the above relation is transitive. In the second statement here, what we are saying is, if one block is above a second and the second is above a third, then the first is also above the third. So, to look at this scenario here, A is above B and B is above C. Therefore, we could say A is above C. An advantage of writing such general statements is of course economy. We need not write all the essential information explicitly. Things could be found out from the given set of facts and the general sentences that I have here. We could record information on on and encode relation between on and above, and we can then avoid having above information explicitly stated. These general statements, if you have by this time realized, is not restricted to the blocks world scene that I am taking here. It is possible to have none of the specific sentences that we have for the blocks world scene true, but still the general statements that I have here would be correct. Now, let us look at another knowledge representation example of a simple genealogy knowledge base. So, I have to have certain predicates and some facts. Here I will only work with the predicates and leave the facts for you to work out through. Whenever we are creating such knowledge bases, we need to realize that we can write facts and rules that attempt to capture all of the important facts and concepts about a domain. So, these are referred to as axioms. We can use these axioms to prove theorems. Now, one point to note is that mathematicians do not want any unnecessary or dependent axioms. One that can be derived from other axioms is something they would not love to call an axiom at all. However, one needs to realize that dependent axioms can make reasoning fast. Therefore, choosing a good set of axioms for a domain is kind of a design problem, and as we go on working through more problems in knowledge representation, we would have a more better understanding of what to be taken as axioms and what to be left out to be derived. So, a definition is an important concept whenever we are trying to write such a knowledge base. A definition of a predicate is of the following form, which says Px if and only if that particular concept is satisfied. And the definition can be decomposed into two parts. The necessary description, at which point it would mean Px implies, and the sufficient description, at which point it would mean that the concept that has been defined implies the predicate. So, let us try and understand how one could define a predicate father x comma y, that is x is the father of y, from two primitives, one called the parent, x is the parent of y, and male x. Now, parent x comma y is a necessary but not sufficient description of being a father. So, someone who is a parent is a father, but parent is a necessary but not sufficient description of a father. If x is a father of y, then definitely it is the case that x is the parent of y. However, if x is a parent of y, it is not necessary he or she is the father. Parent x comma y male, and if we put a third condition that the age must be greater than 35, is a sufficient condition but not necessary description of the father predicate. So, somebody who is a parent and a male and is above 35 years of age is a father, but this does not work on the other way. However, for any x which is a father of y, it need not be the case that x should be greater than 35. So, when we are looking at the definition of father, parent and male is a necessary and sufficient description of father. So, x is a father of y if and only if x is a parent of y and x is male. Let us try to get this by understanding what we mean by the necessary condition and the sufficiency condition one more time. Sx is a necessary condition of Px. What that would mean is that for all x, Px would imply Sx, whereas when Sx is a sufficient condition of Px would mean that for all x's, Sx would imply Px. And when we are talking of a definition for a predicate, then these two must be equal. That is, here Sx is a necessary and sufficient condition of Px would mean that for all x, Px if and only if Sx, and that is what is a definition. Let us now try to get a more concrete knowledge representation of a simple genealogy knowledge base using a couple of predicates. So, we have our first predicate parent x comma y, which says that x is a parent of y. We could have another predicate child x comma y, x is the child of y. We have looked at father, father x comma y would mean x is a father of y. Daughter x comma y, x is a daughter of y. Spouse x comma y. Now, this is an interesting predicate, for you could see that if x is the spouse of y, y is the spouse of x. So, spouse x comma y is a symmetric relationship. We could have husband x comma y, similarly wife x comma y, and then we could have ancestor, descendant, male, female predicates defined, and we could have a predicate called relative. One can think of more predicates. Now, this is where the question of design and the question of how much of the facts to be taken into consideration to create a knowledge representation is to be explored. So, let us try and define a couple of predicates before we include a couple of rules for our simple genealogy knowledge base. So, here is our first definition. For all x, for all y, x is the parent of y if and only if y is the child of x. So, that is the most simplest of definitions that you could have for parent. We have already seen the definition for father. So, for all x and for all y, x is the father of y if and only if x is a parent and male. Similarly, we could have a definition for mother, in which case we will say that x is a parent of y and female x. We could define something like a daughter relation. So, we have for all x, for all y, daughter x comma y if and only if x is a child of y and x is female. So, here one needs to be a bit careful to see that we are talking of x. whereas Y is one of the parent, either a father or a mother. And therefore, for a daughter definition, it is important that X is female. We could similarly include a relation for son, and then we have a relation here for husband. Now, for all X, for all Y, X is a husband of Y if and only if X and Y are spouse of each other and X is a male. Similarly, we could include a definition for wife. One thing to note in these definitions are that while we are doing it, a couple of them we need to consider as primitives, and then using them we need to look at which are the necessary and sufficient condition for the other predicate to be defined in terms of the primitives. Now, let us include a couple of rules. So, here is our first rule, which says that if X is a parent of Y, X is an ancestor of Y. So, every parent is an ancestor. The next rule is saying that if X is a parent of Z and Z is an ancestor of Y, then we have X as an ancestor of Y. And similarly, we could see that we could draw an equivalence between descendant and ancestor by saying X is the descendant of Y if and only if Y is the ancestor of X. Now, here is an interesting rule on who is a relative. So, for any X and any Y, if there is a Z and X and Y share the common ancestor Z, then X and Y are relative. So, this is something like related by common ancestry. We could have another relative definition coming directly from the spouse relation, which is related by marriage. So, for all X, for all Y, X is the spouse of Y, we could say X and Y are relative. Now, this is what we have done in this portion of the representation exercise. We have looked at a simple genealogy knowledge base and tried to understand how we could define predicates, how we could include rules into the system. So, we should take a couple of notes before we end our discussion today. We have seen that while representing declarative knowledge, we write sentences we believe to be true, and those are satisfied by our interpretation. So, the intended interpretation is the model of the sentence we write. In describing a domain, we need to realize that we seldom start with a complete conceptualization. It is neither feasible nor intended that we have a complete conceptualization before we start describing a domain. We rarely list the tuples for every function and relation. For the blocks world scene that I have used as an example here, it was a toy configuration and it was possible for me to list the tuples for every function and relation, but we rarely do this in practice. We start with an idea of a conceptualization and attempt to make it precise by adding more and more sentences as we go about. Now, many of the sentences that we add would be redundant, for they are entitled by the preceding sentences. Now, how is a given sentence entitled by the preceding sentences? This is a part of the notion of logical entitlement. So, what is more commonly called logical inference. We will take up logical inference in our next lecture. Thank you.